So today we're going to be talking about graphing linear equations. Which means we're not just talking about any function at all. I've sort of narrowed it down just a little bit, but we are going to talk about the idea that we can use this for graphing any function. Okay, so what we're looking at today works to graph any function. We just are specifically going to be focusing on linear functions, right? And the idea behind it is, we said yesterday when we made that table and we plugged in input values, how many different values of x could we pick? An infinite, right? And just like with systems of inequality, or not systems, wrong class. Just like with graphing inequalities on the number line, when we had an infinite amount of answers, we said, I can't write those all down, so let's give a graph to show what all of those look like. So that same idea is what we're going for today. When we have so many numbers that we can't write them all down, what are other ways that we can talk about them, look at them, deal with them? And graphing linear equations is one of them. So when we are narrowing down our topic even more, so we have relations. How often is a function a relation?
Always.
Always. How often is a relation a function? Sometimes, right? So we have the large area of relations. We then narrowed that down to the specific type of relation that we called a function. What had to happen for it to be a function? No repeats in the x. And we're now narrowing that down even more. Okay, so these are going to be functions that contain one or two variables. With no variable having an exponent other than 1. What's an exponent? Squared is an example one, right? That little superscript type number. Okay, so no exponent other than 1. How often do we write down an exponent of 1?
Never.
Yeah, we don't, right? So we won't see an exponent at all. So 4x equals 7 plus 2y. Is this linear?
Yes.
Why do you say yes, William?
Because it has two variables with no exponents.
Right? We have 1 or 2. We have 2. And we don't see any exponents, so this is linear. How about B?
No.
Why is it not? Okay, we have an exponent of 2. This is super creatively named. So if it's not linear, we say that it's nonlinear. Now, it actually does have another specific name. And this is actually one of those topics that I think it's easily overlooked that is really important. Okay, math is full of patterns. Those patterns give us information that allow us to take shortcuts or to have a general idea of what's going to happen. Right? Knowing that something is linear or not gives us a big piece of information about what is happening with that as we learn more about linears. Okay, so while this for right now is nonlinear, we are specifically going to be able to give this a label of a quadratic later in algebra, later this school year. Okay? How about C?
Yes.
We say linear?
Yeah.
C is linear. How about D?
Yes.
Linear,
Yep.
right? 2 variables. We feel comfortable with all that info? Okay, so when we go to graph today, again, while we are focusing on linears, this concept works across the board for graphing anything. Okay, it works at any point in time. If you were taking a state test and it says graph something, you're like, oh, geez, no idea how to graph that. This always works for anything. Okay, and the idea is that we can make a table. Keeping in mind that when we make a table, that table can be turned into ordered pairs. That ordered pair can be turned into a graph. Right? That's the process, the sequence we sort of want to go through. Where the rules that we want to have for our table is that we're going to try and get at least 3 points. Okay, sometimes if it's a more complex, like it's non-linear, We might want 5 or 10 points to get a better idea of what's going on. Okay, we don't want any fractions because if we're plotting fractions, we're really going to have to approximate. And how does Mrs. McKinney feel about approximating? Right? Not unless it's a story problem and we're ready for a label. Okay, and it needs to fit on the graph. Because if we're drawing extra lines up here, then we're back to that we're really just approximating. And we want to make sure we're getting a nice, precise answer. Okay, so we're going to create a table, and we're just going to pick some stuff. Okay, we're just going to try something. Now, we could go with the approach of picking your favorite number. So, maybe I'm remembering correctly. I can't remember. What was your favorite number yesterday?
I didn't have one.
Oh, shoot. Who was the number? Someone had a lark. Kate, what was your favorite number?
25.
Oh, yeah, 25. I knew it was somewhere we were on this side of the room. Is 25 going to be a reasonable X value to pick when we are given a 10 by 10 grid?
No.
No, so going the approach of picking your favorite number might not be the most reasonable place to start. What might be a good place to start? Something easier than 1.
4.
0? 0's a pretty nice place to start. Now, I'm going to push this even a little bit more. And some students love it and some students hate it because you really despise negatives. Usually putting 0 in the middle and doing like a -1 and a +1 is a pretty good place to go. It's going to sort of give you what's happening on both sides of our y-axis. Now, I have lots of students like Mrs. McKinney, I hate -1. I'm not picking it. I'm going to pick 0, 1, and 2. And would you be wrong if you pick 0, 1, and 2?
No.
No. I mean, as long as it fits on the graph, you could pick 150, 125, 4,578,000. I'm not giving you a graph that big, but you could pick whichever 3 numbers you want. And then just like we were doing yesterday, we did in the bell work, we're just going to plug those values in. So we're going to plug it into our function rule up here. And so we'll say 3 times -1 minus 4. And what is 3 times -1 minus 4?
-7.
-7. And then we'll plug in 0. Which will give us -4. And then we will plug in 1. Oh. I mean, you will get points on your test that you can just make up some random numbers and plug them in and get an output value. Okay, then we should know that after we do that, these are then the same thing as ordered pairs. Right? This is really the ordered pair, -1, -7. So we can go over here to our graph and we can plot the point -1, -7. Okay, we can plot the next ordered pair, 0, -4. And we can plot the next point, which is 1, -1. What does it look like picture-wise these points are going to make? A line. Would it make sense that a linear function makes a line?
Yes.
Yes. And then my students say, well, why do I need to make 3 points? My teacher told me in the past that 2 points make a line. Well, that is a true statement. Okay, but any 2 points will make a line. So if you think it's linear, but it's not really linear, you won't know until you make the 3rd point. Right? Or if you made a mistake, you need to plot 3 points and go, oh, that's not making a line, and it definitely should make a line because I'm positive it's linear. Okay, that's why I want you to make that 3rd point. Because the statement is true that any 2 points will make a line, but any 2 points will make a line. So if you're wrong or you did something as a mistake, you're still going to think that you're right. Okay, so once we make these 3 points, we then want to create a line. This is also a pretty sensitive topic to some teachers. Some teachers really like nice, neat, perfect lines. How many of you had to like pull out a ruler and make sure you have this beautiful line? Okay, so here's the deal. Even if I pull out a ruler, okay, so if I pull this ruler out and I say I'm touching these 3 points, I could still not end up with a perfect line. I mean, it will look pretty, but that doesn't mean it's going through the exact points it needs to go through. We're going to talk a little bit later in the trimester when we come back from winter break about how to really get that nice, neat, perfect line. For right now, we just want to make sure we're understanding how we can translate this into a line on the coordinate plane. So if your line is not perfect, I'm not going to throw a fit, but it is important that you don't do this. This is not connect the dots. Okay, we need to understand that it is a line that goes across our graph with arrows on both ends. It continues on forever. So I don't need you to pull out a ruler. We're going to learn some more information about making this line actually perfect. Okay. Okay, great. I just did what Mrs. McKinney said. What does that line mean?
That it's a linear.
I mean, it does tell us that it's linear, but I could have decided that that function was linear before I ever graphed it. So what else does it mean?
That's where it's gonna run through. Like all the points will be on the line.
Ooh, all the points. What do you mean by all the points, Drew? I like that wording.
Like any x value you put into the equation,
Uh-huh.
you solve it.
Keep going. Any x value that we put into this function rule,
It will end up being, or the output will end up being on that line.
so how many inputs did we say we would have? Infinite. So this line is representing the infinite number of x and y values that will make this function rule true. Okay, so assuming I had a perfect line and I picked any point on here, it would tell me a correct x and y value that would make that function rule true. There's just so many points that are so close together, it now looks like a line. Does that make sense? Any questions on that? How many of you are just ready for winter break because you're looking at me like dead lumps on a log? Are we alive? We need to go like run a lap outside in the cold.
Yes.
Something, yeah? You need to like quickly step outside during lunch or something so that we wake up. Number 2. 2x plus 5y equals 10. I don't even like that I gave you this hint. This was too nice of me. So I wrote on here to solve for y. Why should we solve this for y?
Y is bigger.
So you can get it. Because you need the x values.
What do you mean we need the x values? Anything weird about what this looks like? 2x plus 5y equals 10. Why?
I don't know.
Does it look like the other problems we've been talking about?
Oh,
Why not?
shoot. Oh, it did not.
It
Wait.
doesn't say y equals. What does a function rule say? Y equals or f of x equals, and this does not say that. So we want to solve this for y.
Ours are different.
Uh-oh. Your papers are different?
Yeah, it's different equation.
Oh. I just opened up my 3 try instead of my true try. Was your first equation the same?
Yeah.
Oh, okay. This one's just weird. Sometimes I get confused as to what class I'm teaching and I open up the wrong folder. Let's try again. Tracking linear equations. Oh dear. Is this the right one? Nope, that's the homework. One second. What is,
I got the
whoa.
answer, guys. Just saying.
I don't even know. I didn't even click on that. My computer is doing its own thing right now.
Well,
Wait it. That's not what I told you to do. Come on. the same though?
Yeah.
Why did we change that for each class? Unit plans. Functions. Okay, let's try again. If this opens. So yours says 4x plus 2y equals 10?
Yeah.
Okay. You got it. Never opens. Sorry about that, guys. Try again. Right here. Oh. Mine's even doing its own formatting thing. Sorry, mine's decided not to open formatted very well, but I think we'll be okay with it. Don't know where that came from, but okay. Okay, so solve this for y because we want it to be in function notation. So remember how we were practicing solving for y? Reviewing solving for y? I told you solving for y was really important. It doesn't go away. This is y. So what are we going to do first if we want to solve this for y? Subtract 4x from each side. Okay, so then we'll have 2y equals what? Nope. Negative 4x plus 10. Then what? Divide by 2. How many places do I want to divide by 2? All of them. We okay with that? What input values do we want to pick?
-1, 0, 1.
Sure. We're going to plug those in. Okay, so if we plug these in, three plus 5 is 8. Five. 3. Then what do we want to do with these points? Graph them, right? Plot them on the coordinate plane. So I'm going to plot the point -1, positive 8. 0, 5.
How did you get 8 and 1?
Oh, instead of 7. I don't know. Why is nobody saying Mrs. McKinney? You can't math today. One, 7, 0, 5. Nope, that's not 5. 1, 2, 3, 4, 5. Can't count on a graph either. 1, 1, 2, 3. And we're gonna draw a line.
Oh, wow. Big change.
Are we okay there?
Yeah.
Okay, then we're skipping the next problem in the notes.
I did
Because
that one.
we have to test by Friday, so we're kind of doing a random assortment of putting things together today. So skip this one. Your table's both printed. I don't know what, mine's just weird. It's not formatting,
Oh,
right?
I was confused. On
You
this.
have the other table, I don't know what mine's doing. Mine's, I don't know. Okay, so number 5.
Another page.
Y equals 3. Yeah, it's just down on another, I just don't know why it's doing that. Like it clearly printed just fine for you. Y equals 3. What do we think we want to pick as input values?
Opposites.
I think we should still be consistent. What would be good input values?
-1,
-1, 0, 1, okay. So when I plug in -1, Where am I going to plug in -1? There's nowhere to plug in -1, is there? So when I plug in -1, what is y going to equal? 3. When I plug in 0, what is y going to equal?
3.
3. When I plug in 1, what is y going to equal?
3.
When I plug in 1,578,000, what is y going to equal?
3.
3. So I'm going to plot these points. -1, 1, 2, 3. 0, 1, 2, 3. 1, 1, 2, 3. And this gives me a horizontal line. You can always make a table, guys, but sometimes it's just easier to just remember that if there's no x, it makes a horizontal. It's always the opposite of the axis. So the y-axis is vertical. A y with no x makes a horizontal line. So now let's look at x equals 3. Oh, x equals -3. You actually have a table to write in. Don't know. What x values do we want to pick? Yeah, do we get a whole lot of choice here?
No.
No. X is -3, -3, or -3, or -3, or -3, or -3, or -3. Because x doesn't get to be anything but -3. So when we plug in -3, what is y?
Don't know. Wait, how'd you get 0?
Because it can be anything we want it to be.
Oh, okay.
Right? When we plug in -3, y can be whatever we want it to be. So y could be -1, 1, 5, 17, 1/2, pi, I don't know.
Maybe apple pie.
Wait, it couldn't be pi because it has a decimal.
I mean, we wouldn't pick it to plot, right? We wouldn't plot 54. So I mean, whatever, you can pick 3 that fit on your graph. And so our x equals line is a vertical line. How do we feel about those? So far, so good?